Now we are going to study an important law, that is Raoult's law. Raoult's law explains us vapor pressure of solutions. The vapor pressure of solution having two or more non-volatile solute, two or more volatile liquids, or vapor pressure of the solutions containing non-volatile solute dissolved in a volatile liquid. So, to understand Raoult's law, we have to know what is vapor pressure of a solution. Vapor pressure of a solution. In general, we can say vapor pressure means the pressure exerted by vapor phase of a volatile liquid. The pressure exerted by vapor phase of a volatile liquid. As we know, most of the liquids are volatile in nature. It means they change into their vapor at room temperature or at higher temperature. For example, water, alcohol change into their vapor, so they are volatile. To understand vapor pressure of a solution, we can consider three cases. In a closed container here, in first case, in a closed container here, we have taken a volatile liquid A. Volatile liquid A can change into its vapor. So, this volatile liquid A, on heating, its particles present at surface, the liquid particles present at surface leave the surface and they change into vapor. Now, these vapor particles strike to the wall of the container, moving here and there and striking to the wall of the container, exerting pressure. With evaporation, after some time, the vapor particles get attracted back to the liquid surface and they condense back to the liquid. So, evaporation and condensation takes place simultaneously, liquid changing into vapor and again changing back to liquid state. A stage comes when rate of evaporation becomes equal to rate of condensation. This is a stage of dynamic equilibrium where rate of evaporation becomes equal to rate of condensation. At the stage of chemical equilibrium, the pressure exerted by vapor phase of a volatile liquid at definite temperature, for example, T Kelvin temperature, is known as vapor pressure of that volatile liquid. So, we can define vapor pressure of a volatile liquid. Vapor pressure of a liquid means the pressure exerted by vapor phase of a volatile liquid at a definite temperature at the stage of chemical equilibrium. So, for example, the liquid A has vapor pressure PA naught. Naught represents pure state. The liquid A is present in pure state in this container having mole fraction equal to 1, because it is only present in the container. So, its vapor pressure here equal to PA naught, the pressure exerted by its vapor particles at a definite temperature in a stage of chemical equilibrium. Now, the second case we are taking, where we have taken a binary solution containing two volatile liquids, A and B. Both the liquids are volatile, one shown by blue and second one shown by red. Both the liquids are volatile. It means both the liquids can change into their vapor. So, their particles will strike to the wall of the container, causing pressure here. The vapor pressure of A, for example, it is PA, and we are considering the vapor pressure of B, PB. As both the liquids are volatile, their vapors will exert pressure which is Pa and Pb for liquid A and B respectively. Now, as per Dalton's law, we know from Dalton's law, we know that the total vapor pressure of a solution will be equal to the sum of vapor pressure of individual components. The total vapor pressure P of solution, that will be equal to sum of vapor pressure of A and vapor pressure of B, that will be equal to P solution will be equal to Pa plus Pb in this case. So, vapor pressure of this binary solution will be equal to Pa plus Pb. The third case where we are going to study solution containing a non-volatile solute B dissolved in a volatile liquid A. So, this solution has a volatile liquid acting as a solvent, and in this volatile liquid A, a non-volatile solute B has been dissolved, shown by blue particles here, non-volatile liquid, non-volatile solute B. As we know, non-volatile solute cannot change into its vapor, but it will also occupy the surface of volatile liquid partially. We can see non-volatile solute also occupies the surface of volatile liquid, and therefore, it will decrease the rate of evaporation. Due to this decreased rate of evaporation, the amount of vapor decreases, and lastly the vapor pressure decreases. So, for a solution having non-volatile solute present in a volatile liquid, the vapor pressure of solution is less than the vapor pressure of liquid in pure state, because the non-volatile solute particles decrease the evaporation, and therefore, vapor pressure also decreases. Raoult studied the vapor pressure of solutions having two or more volatile liquids, and he also studied the vapor pressure of solutions containing non-volatile solutes dissolved in volatile liquids, and he proposed a law named as Raoult's law. So, according to Raoult's law, for a solution of two or more volatile liquids, according to Raoult's law, for a solution of two or more volatile liquids, the vapor pressure of each component is directly proportional to its mole fraction. We can understand it taking a binary solution of two volatile liquids A and B. To understand Raoult's law, we are taking a binary solution of two or more volatile liquids, this one, having liquid A and B. According to Raoult's law, the vapor pressure of each component is directly proportional to its mole fraction. So, vapor pressure of A will be directly proportional to its mole fraction in the solution, and vapor pressure of B will be directly proportional to its mole fraction in the solution XB. So, for a solution of two or more volatile liquids, the vapor pressure of each component is directly proportional to its mole fraction. Now, if we take the equal sign, Pa will be equal to constant into Xa. To get the value of this constant Xa, we are considering the pure state of A. So, we are considering the pure state of A. In pure state of A volatile liquid, what will happen? In pure state of A, the vapor pressure of A will be Pa naught and mole fraction of A will be 1. If we apply the Raoult's law, the vapor pressure in pure state of A, that will be directly proportional to its mole fraction. Vapor pressure will be directly proportional to its mole fraction. From this value we are getting mole fraction, we know that it will be equal to 1, because only A is present in the container, we have taken the pure state. So, only A is present in the container, and therefore, we can say PA naught is equal to constant. On putting the value of this constant into equation 1, we are putting the value of this constant into equation 1, we get from equation 1 PA is equal to, in place of constant, PA naught into XA. So, we can give one more statement of Raoult's law, that is, for a solution of 2 or more volatile liquids, the vapor pressure of each component is equal to the product of vapor pressure of that component in pure state to its mole fraction. So, we can define the Raoult's law, that for a solution of 2 or more volatile liquids, the vapor pressure of each component is directly proportional to its mole fraction, or the vapor pressure of each component, each volatile liquid is equal to the product of vapor pressure of its own in pure state to its mole fraction. Now, if we have taken the solution of binary liquids for a solution of 2 volatile liquids A and B, PA will be equal to PA naught into XA, and PB will be equal to PB naught into XB. From Dalton's law, we know that P solution is equal to, P solution will be equal to PA plus PB. And therefore, we can write down, putting the value of PA and PB here, putting the value of PA and PB from these two equations. P solution will be equal to PA naught into XA plus PB naught into XB. Putting the value of PA from this equation and PB from this equation, we are getting the vapor pressure of solution is equal to the sum of vapor pressure of both volatile liquids, PA naught XA plus PB naught XB. This is the mathematical expression of Raoult's law for a solution of 2 binary liquids, for a solution of 2 volatile liquids. So, this is the mathematical expression giving Raoult's law for a binary solution having 2 volatile liquids A and B. Now, those solutions which obey this Raoult's law at all concentrations and temperature are termed as ideal solutions, and those which do not obey over all range of concentration and temperature to this law, they do not obey this law at all concentrations, they are known as non-ideal solutions. So, ideal and non-ideal solution we can study in next class. Thank you.